Hello everyone, welcome back. Today we are continuing to look into closed-loop optimization. In particularly, today we are going to go through surrogate modeling. We're going to discuss how does Gaussian process regression work? Why do we use it? And if we use a Gaussian process regression model as a surrogate model, how is the model being updated? Let's dive in. So we were talking about the Bayesian optimization, which is a widely used closed-loop optimization strategy. We use a Bayesian optimization because it's very powerful to fit and optimize a black box function, and that would allow us to link the input parameters of our experiment with the output. In this case, often we have a small data set, and we may also have a very noisy observables. So the idea of building a closed-loop optimization framework, and it is that it relies on making predictions. So we predict our outcome of the experiment before running a lot of costly real-world experiments. So the question becomes, how do we guess the shape of an unknown function from just limited data? Here are some concepts. So the way we do it is to build a surrogate model. A surrogate model is an approximation of the true objective function. Often it's a computationally cheaper one compared to actually running the more expensive real-world experiment. One of the most popular surrogate models used in Bayesian optimization is a Gaussian process regression model. So Gaussian process, it is a probability distribution over possible functions that fit a set of points. You may have heard of Gaussian distribution or normal distribution, which is a probability distribution over possible numbers of vectors. So here the Gaussian process, we are talking about probability distribution over possible functions. And a Gaussian process regression model, or we call them GP regression model in short, it provides both the prediction values. So this is the predictive value, which is typically we use it as a measure of our expectation, what is the outcomes for the experiment we haven't done. And it also gives uncertainty estimates. Sometimes we use confidence intervals to indicate this uncertainty. So this is very handy because once we have the predictive means and our uncertainty estimates, we can use this information to design the next round of experiment. So how does a Gaussian process regression work? So imagine we are a thin film fabrication engineer, and we are interested in tuning the temperature of fabricating our thin films, and then we're interested in optimizing our property of interest. So in this case, the real function that captures how our property of interest changes as a function of temperature is this blue curve. But of course, before we've done any experiment, we don't know what this function looks like. So in this case, we'll have a min, this dashed orange line is called a Gaussian process prior. So we have a prior min, and then we have the uncertainty, in this case, as noted in the form of 95% of the confidence interval. So this is our prior. Of course, then we start to take the experiment, we start to take data. In this case, imagine if we conduct an experiment at the temperature of this yellow dot, and we measure the actual property of interest. The Gaussian process regression model now is updated. So now we have a GP posterior mean, which again is this dashed orange line. At the same time, you can see we have uncertainty estimates. So in this diagram, we show with just one data point collected, we see it's the 1 sigma and 2 sigma, so it's the 68% of the confidence interval as well as 95% of the confidence interval. So you can see why it is interesting, because now we can start to collect more experiments. In particularly, here we have 2 experimental points being collected. And you can see now the dashed line changes, and we have our uncertainty estimates changes. And the third point being collected, you can see is like now our posterior mean is getting closer and closer to the true function that is the underlying this data we've been collecting. And after 10 observations, so in this case, we've already collected 10 data points, and you can see that the Gaussian process regression model fits pretty well with the underlying a true function. And in this case, we've built a probabilistic surrogate model, and you can see how accurate they are by looking at what is the posterior mean, is the predicted mean, and also we can look at what is the confidence interval. In this case, we can see it's we become more and more certain our surrogate model describes the relationship between the input and output. To build a Gaussian processor regression model, let's now look into how Gaussian processes work. So imagine we have our parameter space, and for given temperature, so given x, there is a range of different property of interest values when we experimentally find our measured values are. And we assume they form a Gaussian distribution in terms of the likelihood and what this measured property of interest are. Similarly, at a different temperature, we have a similar distribution like that. So you can see as we start to sample at many different temperatures and making a continuous function, we start to draw these dots together, forming a function. So before we start to actually conduct an experiment, we already have many Gaussian process prior distribution with the sampled function. They are all the possibilities of the functions that would describe our input and output relationships. At this stage, you may be interested in knowing how one data point is related to its neighboring data points. And this is accounted by something called a kernel. So a kernel, also known as the covariance function, it defines the similarity or the correlation or smoothness between the points in the input space. So this is also a chance when we are trying to build a Gaussian process regression to input our prior knowledge about what we think the function between our input and output look like. For example, you may say my data have a strong linear relationship, so maybe linear kernels are more appropriate. Maybe the function supposed to be a periodic function, and we can use the periodic kernel, and also the radial basis function kernel is a popular choice when it comes to trying to fit a black box function. So different kernels can be applied, and they capture various levels of the patterns of the data. And in this way, when we have our own problem, we can put in our prior knowledge about the parameter space in the form of choosing a appropriate kernel. So in this lecture, we haven't really gone through the mathematical formulations of the different kernel functions. So I recommend reading more on this amazing website, which gives a visual exploration on how to understand the Gaussian processes and how to select the kernels. So now let's think a little bit about the broader content. So we are trying to use a Gaussian process to help us to build surrogate models. And Gaussian processes are great. They are non-parametric. They are flexible. So we don't have to know what is the function that describes our input and output relationship. We can try to fit a surrogate model. And very importantly, we now not only have the predictive mean, we also get the uncertainty estimates. And it works very well with the small and noisy data sets. But the Gaussian processes are not the only surrogate models we can build. Often there are other common alternatives. For example, the random forests or support vector machines, or if you have more data based in neural networks, maybe more suitable. So these alternatives often can overcome the computational expensiveness of the Gaussian processes, but also often they have the drawbacks, where having the uncertain estimates is not as easier as if we use a GP-based surrogate model. With that, thank you very much for listening, and see you next time.